for coming today. My name is Rick Hahn. I'm a professor in the School of Computing at Macquarie University, and I'll be talking about various research projects we have in autonomous drone systems. Um, this is sort of next generation sort of the technology, so it may not be immediately available commercially, but the idea is that hopefully sooner or later it will be coming down to a manufacturer near you. So where is Macquarie University? We are in Sydney, Australia. We're sort of near the northern part of Sydney. This is a picture of our beautiful campus. And in fact, we actually fly our drones near the lake over here because this is one of the open spots on campus. Okay, so a little bit more about the School of Computing at Macquarie University. As we can see here, a head of school likes to boast about how our ranking has improved, the research ranking of our computing school. And according to the Times Higher Education, we were starting around 250 when I joined Macquarie in 2021. And it's all because of me that, the rankings have improved to 125. But no, I mean, in all seriousness, we're very pleased. We have many hires, and we're very strong, I think, in AI, ML, artificial intelligence, machine learning, data science, natural language processing, security, and mobile computing. And one of the other recent hires is Tao Gu, who was the chair of ACM Mobicom, one of the major sort of technical conferences in mobile computing and computer science. And so he is also an IEEE fellow. And so overall, we're quite proud of the fact that at Macquarie, our mobile computing group is #1 in Australia in terms of our research publications at the top venues and recognized sort of worldwide. Okay, so now let me talk to you a little bit about our drone lab. So here is shown some of the people in our drone lab. We have PhD students, we have postdocs, we have the three of us over here on the right. This is me in sort of the light shirt, and right next to me is Andrew Quantama, who's a professor, and then we have Professor Subhas Mukhopadhyay. He's an IEEE fellow as well. We have some of our industry partners here, and then over here on the left, if you go to our mqdronelab.com webpage, you'll see many more faculty that we have who are conducting research as part of our drone lab here at Macquarie. These include two more IEEE fellows, Ian Collins and Stephen Hanley. They're both sort of wireless networking communication gurus. And we also have some very interdisciplinary sort of a faculty. We have Professor Jane Williamson of biology. She's interested in using drones to monitor sharks and rays on the Great Barrier Reef. We also have Professor Judith Dawes of photonics, and so interested in lasers and drones. Okay, so here is hopefully let me turn down this a little bit. This is a quick view of our drone lab. We actually build our own drones from scratch. And so we don't just buy DJI off the shelf, which is, fine. But as researchers, we're really sort of, devising new innovative drones. And so we have our own 3D printers. We have our own calibration rack that you saw earlier. And then we have our own flight facility. And so this is where we actually can fly the drones indoors before we take them outside. And so it's very nice to have our own warehouse. So you see it's a very vertical, it's very important. It's not a lot of universities actually have this. And so we're pleased to have all of this. Sort of the door that you saw in the background there is actually an example of our lab is right next door to the indoor flight facility. So we can very quickly build a drone and then test it indoors. Okay, what are some of the research projects that we have going on? We have four main pillars of research in our drone lab. We're talking about autonomous drone systems because we think they should not have human intervention in the future, or less and less human intervention. We're very interested in swarms. That is, what can you do with teams of drones? And I'll show you two projects that we're working on here at Macquarie. We're also working on high performance drones, drones that fly longer and can stay up and can go greater distances. So we have a $2 million project with the Sea Flight on sort of more aerodynamic design of fixed wing UAVs. And then we also have some research that we're pursuing a patent on that tries to improve the motor efficiency of drones. And we think we can improve the efficiency by up to 30%, which would mean that you should be able to fly for 30% longer. And then the final area that there's a lot of industry interest in is safety. And that was alluded to by our previous speaker as well, that drones can crash into people, they can injure people, they can destroy property, and the reason is because the drones themselves are very complex. For example, shown here is some software that we've built for auto landing drones, autonomous landing of drones. And it's very complicated. There are many different components, and any one of them can fail. And so this can cause a catastrophic crash. And so this is very important. This is an element of the research that we have. So the first project I want to talk about is our collaborative drone swarm lift and transport. And so we sort of showed here, we have two drones and they're lifting a payload together. And we think that this could very well be the future. And so this research was a finalist for a Best Paper Award at the IEEE ICARM Robotics Conference just recently in 2024. So what we're addressing here is that each individual drone can only lift a certain amount of weight, okay? And there's only, usually these are small drones, so there's not a lot of room to sort of put an additional payload. And so we said, what can you do if you were to combine multiple drones to sort of be able to lift more weight? But in order to do that, you first have to solve a couple of problems. The first problem is the balance problem. And so here we only have one drone. And you see that our student Avishkar has put a small bottle cap on here. But when he puts it on an offset way, you see suddenly the balance is off. And when it's completely sort of off, as we'll see up here, he actually causes the drone to crash into the ground right there. The second problem that we have is that there's a lot of downdraft to these drones. And so you see it right here. There's a great deal of turbulence underneath the propellers of the drone. And so this combination means that when we want to build a sort of group-based cooperative lift, that we have to take into account both turbulence as well as balance. So our initial idea with sort of cooperative lift was that we would have a pallet that would hold the objects that we wanted to lift, and then we would attach the drones to the different sides of the pallet, and they would lift together. This is a very complex control problem. They have to keep it balanced as they're trying to transport their payload. Now, this particular approach already you can see some problems with because the payload is underneath the propellers. And so there's going to be a lot of complex wind dynamics underneath here that the payload is going to be subject to, and it's going to cause a lot of strange behavior. So what we said instead is, why not move the payload and the pallet above the propellers, as shown here? And so in this example, the control algorithms that need to move the payload now can be much simpler because we don't have to also deal with the interaction between the payload and the wind effects of the turbulence. So we call this approach push-based lift in comparison to the pull-based approach over here on the left. Okay, so we've actually built this system. And we started out with two drones, and we hope to expand to more drones in the future, but just to prove the concept. And so shown here are two of our drones, and then we have our plate in between that is holding our payload. This plate we call it SBT, or sort of a self-balanced tray. And what it has is a couple of sort of three degrees of freedom sort of servo motors here that can adjust the level of the plate between the two. And so we have one on the right and we have one on the left. And so this will maintain balance. Also, the drones have LiDAR attached to them, which means that they can hold the same altitude. And so, and in addition, they have GPS and many of the normal sensors for a drone. Okay, if we were to drill a little bit more deeply into how this all works, if we look from the top down on the plate over here on the right, we see that's divided into sort of sectors. And what this tells us is if you put a payload on the plate, what is the center of gravity? Is it unbalanced? So for example, here, this is slightly off balance. It's not in the center of the plate. And that's useful information because we use that information to feed into the control algorithm. So here's our resistive plate, and we will feed that into an Arduino, which has a controls algorithm, a PID controller on board, and it will compute what the amount of a correction that needs to be made for each of these servo motors. Now, shown here is a servo motor, and we have control over 3 degrees of freedom, the pitch, the roll, and the yaw. And so we have control of that over both ends of the plate. And so what happens is we have a lead drone, and the lead drone will do the calculation, and then it will communicate over Bluetooth to the follower drone, and tell the follower drone, this is how I want you to actuate the servo motors on your side of the plate. And that way we maintain balance. Now, in addition to that, we have our normal Jetson Nano on board these drones, and that controls the flight controller, which then tells where the drone should move or where the drone should hover. Okay, so here's a demo of how this actually works, and to prove to you that we actually got it to work. And so the student here is, our PhD student is putting a dynamic load here. It's not even a static load. It's a bottle of water. And we see that our 2 drones are able to sort of lift this together and to transport this. And we see Alice over here. She's actually feeding remote control commands to the lead drone, which will then move the whole group together. And so this idea has been patented, it's been published, and then we're working on the next generation version, which will have more drones and be able to lift more weight, and will be even more autonomous, and that we won't need to use remote controls at all. Okay, so that's the first sort of drone swarm project. The second drone swarm project, or a drone team project, involves emergency battery services. I noticed that our prior speaker mentioned limited battery time as a problem for drones, and that's what we're addressing with this project. So this project was just sort of presented last week at the ACM Mobile Computing Conference, which is a top conference in mobile systems. And that's why I'm here in the United States right now. We're presenting that at the conference. Okay, so we're driven by many of these applications of drones, whether it's aerial surveying, package delivery, or even precision agriculture, as was mentioned in terms of the Mekong rice growth. And all of these have limited battery life. Typically, the drones can only last, if you're lucky, 45 to 60 minutes, but more likely only about half an hour. Even in some cases, even if you add more, battery life, as shown here in this graph, that doesn't necessarily give you more time, flight time. In fact, the more battery you add, the heavier your drone, and that can actually lead to less flight time. We have it's likely that for the foreseeable future, we're going to have this problem, because Moore's law is not applying to battery lives. It's not doubling every year, our battery capacity. It's only growing incrementally by some, 10%, per year. So what are the ways that people deal with limited battery life on drones? Well, they try to buy bigger batteries, but there's a limit to what you can do there. Another one is they do ground-based battery swap. And so they will fly back to some base station and then swap out the battery, or they'll fly back to some base station and do some wireless charging. Now, the problem with those approaches is that the drone has to leave, the field. wherever it's doing its work. And so in certain cases, this may be okay, but in other cases, like if you're tracking a target, then that's not okay. There are some cute approaches where we had a flying battery that actually lands on top of a drone, but this flying drone is much smaller than the main drone that needs the battery, and so this actually doesn't work very well. Another option is just to buy more drones, and so if one drone's battery runs out, you just fly a second drone in there. So that requires you to spend a lot more money and then also manage a lot more drones, which is a big headache. Finally, we have one prior work that has tried to do mid-air battery swap by dropping the battery from a top drone to the bottom drone. But as we saw, there's a lot of downdraft turbulence between the two drones. And so they have to be separated by 5 to 7 meters, and which makes the accuracy of the drop more uncertain. So we said, let's experiment with the idea where we do sort of mid-air battery swap, where we have a mother drone with a fresh battery, and it will come near another drone that's in the field, and we will swap batteries in midair. We will give a fresh battery to the drone with the low battery, and then we will retrieve its sort of worn out battery instead. And so this approach has a lot of advantages. This means that your drone can now stay in the field almost indefinitely, subject to the mechanical breakdown of that drone. Also, it means that we are bringing the battery to the drone rather than forcing the drone to fly back to a base station to get a new battery. And so this means the drone can continue to do its tasks in the field. Also, because we're swapping the batteries, then we don't have to, we're not adding any more dead weight to the drone because we're taking away the dead battery. And so we call this emergency battery services, or EBS. And we think this is going to be very common in the future, sort of as an additional feature for drones. So we eventually sort of built this approach, and sort of I will show that in a second here. But basically, we have a slide which will allow the battery to slide from one drone to the other drone. And the trick is, how can we get these two slides to align in midair? And I'll show you how we do that in a second. So we have to get the drones close together. And so that's one of our contributions. We have to figure out how they sort of approach each other and navigate towards each other. And then how do the slides sort of meet so that, we call this the last centimeter challenge. All right, so, we already mentioned that the drones, when they're near each other, there's a lot of sort of turbulence. As you can see in this example right here, the drone underneath is pushed away by the turbulence when they're directly on top of each other. But what we found out was that you can actually overlap the drones by almost 50%, not 100% where they're directly on top of each other, but if you overlap like maybe only half of the propellers, you actually are able to get relatively stable the drones somewhat near each other, and the displacement is not nearly as bad. And so we use that to our advantage, because what this allows us to do is us to get within 0.5 meters of each other, which makes the docking a lot easier. And so the actual orientation and sort of docking is achieved by putting markers, visual markers on the receiving drone. And so what we do is we put a unique marker that can be identified by the top drone, and so it knows which drone it's doing the battery swap with. And then we add 4 extra small markers, front, left, right, and back, that help you determine, these are all unique, exactly your orientation, the top drone's orientation relative to the bottom drone. And so it will know if it's in the wrong place, it has to sort of move around until it's perfectly aligned. Also, because the size of the markers, it knows the distance that it is from the drone. And so when all of these factors align, when all the markers are correct and the sizes of the markers are correct, then you're in the right place, and the two slides can come down, and you can connect and transfer the battery. So let me show you. We built the system. We built the top drone with a slide. We built the bottom drone with the markers and the slide, receiving slide. And then let me show you that it's sort of, we're out by the lake here, and you see that we're able to sort of transfer the package from first drone to the second drone. Now, what we could have done is, try to make this more perfect and make a really smooth demo or that kind of thing. But we felt the most important thing was that they were able to get, the two slides are able to get close to each other, and the rest is just not as important from a computer science point of view. Over here on the right, we're actually seeing an actual battery being transferred from one drone to the next. So you'll see this over here. There's an actual battery sort of going across the slides. Okay, so that's the Aero Bridge. The final thing I wanted to talk really quickly about is that we're also working on autonomous drone landing. This is a recently, it's about to be published a work, and this is in conjunction with an industry partner called Skynet. And the problem is that drones, they don't know how to land autonomously. Not even Google or Amazon have solved this problem. And that's because if you look at this picture and you want to sort of, land, that basically it's very difficult to figure out what is a safe landing spot. If you were to look here, yeah, maybe you could say, here's the driveway, and maybe that's okay to land there. But right over here on the street, it's a flat, location. You could drop your package there. But if you were to land there, you could get hit by a car. And so you have to teach the drone using AI and machine learning, what are good places to land, what are bad places to land. And this turns out to be a difficult problem. And so what people have done is they've deployed markers to help assist the drone to land. And so DJI does this as well as many other manufacturers. But even there, the marker assisted landing is not perfect. And so, for example, shown here, we have two problems. The first problem is we have a false positive where it actually thinks that this is the marker that it wants to land on, but actually it's the wrong marker. And over here, we have a false negative on the lower left, where it sees it fails to see the marker, even though we can see the marker as human beings. The AI software, the image recognition software, cannot see it because of the sun glare off of the marker. And so we've developed an AutoLand sort of software system with our industry partner, and you see it's fairly complicated. There's marker detection, there's obstacle detection, there's path planning. There's a lot of pieces that can fail in order to do this marker assisted landing. And so this could be caused by bugs. And so the industry is very interested in making sure that the drones are safe to fly and the software is as bug-free as possible. Now, you can do practical real-world tests, but you can only do so many real-world tests. In simulation, you can do millions of tests, so it's very scalable. But you have to make sure that your simulator is accurate, okay? And in fact, we actually try to reproduce the findings of our simulation in the real world. Now, I won't go into too much detail here. I'll just say that we have a approach that uses genetic algorithms in combination with reinforcement learning that will generate test conditions that will try to break the software in a very efficient way. So this is how we sort of combine the two together, the genetic algorithm plus the reinforcement learning. I won't get into the details here. I'll just say that the technique overall has been very effective at finding ways to break the AutoLand system. For example, maybe it's rain that causes the sensors to fail, or maybe it's because there's a person that's walking near the marker while it's trying to land, and that causes the AutoLand system to fail. So we've been able to find these failures much more effectively using our GARL approach compared to a bunch of different baselines. When we looked at sort of we tried to classify all the different failures. We said some were false positives, some were false negatives, some were due to static collision, others due to dynamic collision. And then we also found some bugs in the actual planner software itself. So we tried to reproduce this in the real world. We saw we were able to reproduce all of the bugs that we found that we predicted in the simulation world. We were able to reproduce them in the real world by flying our drones with our software. This includes the planner software bug that's shown here at the bottom. Okay, so that's a very quick survey of 3 research projects that we have in autonomous systems. 2, we're dealing with drone swarms, the drone swarm lift and the mid-air battery transfer. And then the 3rd one is dealing with autonomy in terms of safe autonomous landing. And with that, I hope I kept my time. So
Perfect.
happy to take questions.
Fantastic. Richard, that was so interesting. I was kind of like concentrating so hard on the presentation because there's a lot of new information in there. As you said, next generation sort of type of research. So it was also one of those presentations where you sort of sit there and think, wow, uh, so let me catch up a little bit. I've got quite a few questions, but I'm also sort of still processing some of the opportunities that some of that research presents as well. So I guess that's one of the questions I could sort of imagine in an agriculture sense, and you're getting lots of positive feedback there too from the audience, of the swarm lift type approach in agriculture. So have you been thinking about that from an agricultural perspective around how that could be used? I mean, I'm thinking particularly in sort of more isolated areas or areas on a farm, for example, that are quite difficult to get to. That could be actually really useful. What are your thoughts on that?
I would be interested to hear what Kwong had to say about that. But I mean, we're offering the capability, and we think that it would be useful in a variety of scenarios. We thought, like in construction, for example, you're often lifting a lot of heavy like boards and such onto the roof. And if you had a bunch of drones who could very quickly just in a cheap way provide lift capability and move something from this place to the other place on on a construction site or on a farm, that to me that seems pretty easy, because you can't hire a helicopter, whenever you want to do this, and moving stuff across a muddy field could be, really painful. And so this kind of transport capabilities, I think, low cost and flexible, we would hope, as long as the software is working properly, so this group autonomy is a very interesting concept that we think is well worth sort of exploring in the research context.
Yeah, it's fantastic. And we will ask Kwong at the end just maybe his thoughts on some of this. So Kwong, just be ready if you're still there. I can see you, I see you're there, but I'm going to ask you what some of your thoughts on how this could be used as well in the Mekong, for example. We hear quite a bit around repair issues and breakdowns of drones, and I've heard of examples of farmers going and buying drones and then they break down after a couple of uses and then they can't repair them. And so when you're designing your drones, and you showed us some pictures in your lab at the start, I mean, are you really thinking about that aspect? Because it seems to me quite important, particularly in some of these countries that are bringing these drones in, sometimes in remote farming areas, and then they use it and then they can't fix it, and then it costs a lot to get fixed and they don't have the material. So is that part of the design work?
Yeah, I think robustness, reliability is a big safety issue for the drones. And so that gets maybe more towards the hardware robustness side of things, as opposed to the software robustness, where we've been putting most of our effort. But they're both equally important, because once a drone fails, it fails. And so we've certainly run into issues with propellers. We've run into issues with motors, GPS being off or something, just the sensors not working, not being calibrated properly. And so all of this sort of just to keep the drone in balance, we have to, when we're building it from scratch, it has to be very carefully calibrated. And so I can certainly imagine someone who's buying some off-the-shelf commercial thing, and it just stops working, because it was left in the rain, and something short-circuited, and so and there's no expertise on hand, and so it's not robust. And so yeah, I could imagine that that would be also a good area to be robust. Sorry, for researchers, but generally as researchers, we're kind of about 5 years ahead of where the drone manufacturers are, in terms of the more pie in the sky kind of
That was my next
ideas.
question around how long does it take really from your work here to actually commercialization? I guess it depends really on
Yeah.
what the service or product is that you're designing, but you 5 years ahead, do you think, of the
Yeah, technology transfer is definitely a big issue. So we've patented, both of those ideas that you saw, and
yeah.
we're working on commercializing the battery swap idea as well.
And
And so,
can you see that battery swap idea? I mean, how would you see that in the context of farming?
well, I mean, it would be able to extend, the lifetime of any sort of like, if you're deploying um, uh, you know, these the fertilizers or the pesticides, that drone that's doing that can stay up longer,
Yeah.
so you can just have a companion drone that comes by and says, oh, you're down to 20% battery, time to swap out your old one, here comes a new one, and then you just keep
Yeah.
going, and
Yeah.
you don't need to sort of fly that drone back, or you don't need to buy a whole bunch of extra drones that can do that, because those must be expensive drones, right?
Yeah.
So I think this is especially beneficial for the high value drones that are out there, that they would be willing to pay for this sort of premium feature. Because I'm not sure I would see that for just your average hobbyist. They probably don't need this battery swap capability, but I think for agriculture, it probably makes sense.
Yeah, that's great. Thank you. We've had a lot of discussion around the need for stronger regulation in the sort of new area of drones and agriculture. And I guess what's quite interesting for me is that it seems like we're a little bit behind at the moment, which is often the case when a sort of new technology comes on, although it's been around for a while, but as it bursts onto the scene and then more and more people start using it and it starts scaling out, and then regulation sometimes has to catch up, which is kind of what we see is happening in Southeast Asia. I guess what's quite interesting for me as well is as you're designing the sort of next generation sort of applications, are you also thinking about the sort of regulations that might have to sit aside those? Because I think they would be quite important, particularly when you're talking about autonomous drones
Oh
and
yeah.
some of these others. And also AI. So that's another question that a lot of people have is just around where do you see AI sitting in this? And that's also with the autonomous drone sort of technology, I guess,
Yeah, well,
in the future and regulations. Are you
I
thinking
mean,
about regulations now as you're just, or are you just sort of focusing on the pure research of the design of the drone? But is that something that you need to keep in mind?
no, definitely thinking about regulations all the time. There are all sorts of issues that are sort of, you know, these autonomous drones, and then you add autonomous drone swarms to that.
Yeah.
And so we haven't even sort of gotten our minds wrapped around how do we make sure that these autonomous drones are not a threat. And then, oh my goodness, now we have coordinated autonomous, drone swarms. This could make the threat even worse, if that could be the case, but also can make, technology is always a double-edged sword. And so it could also be very beneficial, in certain applications. And so the two examples I shown here, I think fairly beneficial, but they could be abused. And so, but we're definitely thinking about, how can we talk with government regulators about, you know, uh, you know, are they willing to sort of at least allow us to experiment in isolated sort of cases with some of these concepts, not necessarily unleashing it all at once on the public, so certainly we're aware of many of the shortcomings of drones, the privacy issues, the noise issues, and of course the injury issues as well. And so, definitely it's a big part of. That's why, when I was showing the picture of all the people who are interested in our drone lab, that includes like a law professor who's interested in sort of the privacy implications of drones. So.
Excellent. Thanks, Richard. And I'm just gonna, Kwong, are you still with us? Could you unmute yourself and can we see you if you're there? Just see if
Yes,
here we go.
I'm still
No,
listening.
I was just interested. Is there any comment? I mean, do you just your comments on that presentation would be really interesting.
Yeah, very interesting. It's a swarm drone. I have heard about swarm drone, and but swarm leaf drone I first heard from Dr. Richards, and other three topics very interesting. And I think for the swarm leaf in the Mekong Delta is very useful, because in the Mekong Delta we have a lot of river, and the road system is still already improved, but for heavy load like fertilizer, pesticide, or like seed, for seeding, we need to have like, if farmer would like to move the fertilizer across the river, they take longer time. And if we have like a swarm drone leaf, then very useful, and reduce a lot of cost for farmer, and also efficiency will be higher in combination with the spraying or other thing. Yeah, that's my comment, and thank you for your presentation. Very interesting. Yeah.